use simple pseudo-random number generators for calculators.
First one.
I always quote my favorite French writer Voltaire, who says, "The better is the enemy of the good." We're always trying to get to do things in a better way. And my dedication is to the grandchildren, Owen and Grace. They are exceptional people, and they will have great potential when they are adults.
You're not biased, of course.
Of course. About floating points PRNG, which is what we're doing here, where you use floating points from start to finish. It's really an art with a lot of luck. Comparison with integer-based, where you're using integer operations, except for the very last step where you divide a resulting integer with a possibly bigger integer, then those are you can move them around to other systems and all that. Here you are at the mercy of the number of digits supported by decimal real numbers. I call this Project 997. Why?
Good name, by the way.
Yes. The HP Stat Pack uses the following equation here, where you take an old random number, multiply it by 997, take the fractional part, and get a new random number. And in HHC 2017, I showed that this algorithm was the best legacy and simplest algorithm compared to what else HP used, like adding pi and raising to a power. Those didn't do real well compared to this. So the question is, can we do better in a somewhat more general form, generalizing 997, replacing it with B and adding a shift? This way, this can handle a zero initial a random number, although I don't recommend it, but still. So we're going to measure our measure of the goodness of the random number generated is something what I call the penalty factor that I also introduced in 2017. And it's calculated and dependent on a batch number of random numbers and the size. So we're going to stick with 10,000, which is ample for the calculated applications. The penalty factor basically performs several tests and then takes the absolute value of the result of the test, subtract from it the expected theoretical value, and then multiplies it by a factor, adds all that up, and you get that. So the lower the penalty factor, the better you are. For example, the expected mean of a random number series is a half. So the closer you are to 0.5, the better you are. We're going to do two approaches. The first approach, we're going to use optimization, because I can use the penalty factor to optimize it. So we're going to use the penalty factor. We're going to optimize the augmented form here for the values of A, B, and the initial seed. The initial seed does play an important role in the quality of the sequence that comes with it. I'm going to do two approaches. I'm going to use a very good evolutionary optimization program, the particle swarm optimization algorithm, and I'm going to use dumb luck simple random search and see if that does terrible or, for its relative simplicity, still does okay. The other approach is we're going to calculate penalty factors for educated guesses for A and B. I thought I'd put my smart pants on and see how lucky I can get. Now I'm using MATLAB here, and I've implemented 10 decimals rounding, which I didn't do in 2017, for the random numbers, and fewer decimals for A and B. This will make the results hopefully work better with vintage calculator like the 41C, 42, and maybe even the 67. The schematic, we have really two stages, stage 1 and stage 2. In stage 1, I take the values for A and B and initial random seed in a wide range and try to find the optimum value, and then feed them back to get narrower values of A and B. and then feed those results to stage 2. Or I can get the educated guesses of A and B and do the same, and then get the results and compare what I get from here with what I get from here. In the optimization approach for both phase 1 and 2, I have the range for A is 0 to 1. It makes no sense to go higher because the fraction function will chop it off. The range for the initial seed, I try to be a bit reasonable from 0.1111 to the 9s here. But in the range of B, I try to be creative. From 100 to 2,000, this will include and surpass our beloved baseline 997. Or from 100 to 20,000, or from 100 to 200,000. This is like if there's a black swan out there, we may find it, you know. What I do is I make 250 samples to calculate penalty factors. So I have 250 of those, generated from sets of 10,000 random each. The calculations took about a day. I had several laptops and they were running for most of the day. And I programmed them that then when they're done, they shut down automatically. So I don't have to check in the middle of the night if they're done or not. I did not want them to overheat too. In the second phase, I take the optimum value and I create somewhat narrower intervals. What I do is I take the optimum values of A, B, and the initial seed, multiply it by 0.9 to get the lower range, and by 1.1 to get the upper range. So these are tighter intervals. Again, I do 250 samples each, and I calculate the penalty factor. So it's 250 times 4, 10,000 random numbers each. Now the statistics for the results from stage 1 and 2 are, I get the mean and standard deviation, of course, number of observation naturally, then I get the minimum and maximum values and the range. Now, the maximum values gives us an idea of how bad things can get. But don't get too hung up on the minimum and maximum because they're more for the optimistic and pessimistic. And the reality is in between somewhere. And to get to that, I calculate the confidence interval for the mean at 95% confidence, that's the delta. And then I add and subtract with the mean and I get the upper and lower confidence range for the mean. This is where my money is. This is important algorithm qualification, especially the upper limit. It gives me an idea about the average worst mean penalty factor. That's what the stuff that I will most likely deal with. So this is what I'm looking for. Of course, I also get results for the A and B used in the algorithm. And the best seed for the random numbers, XR and D, I call it that. This value will give me the minimum penalty factor. So I have 14 algorithms. The first 3 are variation of our augmented formula here. The second one is the baseline test. That's 997 times R. We want to see how good it does versus everything. The third one is the one Angel Martin used in his random ROM, and I believe I think it belongs to Jean-Daniel Dodin in one of his books. I think he copied it. I'm not sure, but we'll do just a simple test, which, giving you a heads up, it does well. Then I have these hunch algorithms. I go back to the 997 and I add pi to it. And I say, will it do better? Then I go here, since 997 is 3 numbers short of 1,000, I said, well, how about if I take 1,000 and add 3 to it and see how that form does without pi and with pi. Then I have 2 of these with 11011 are straight, and then I add pi to it. And then the 9977 times R without the pi, and here I add pi, and then 9997 times R without the pi, and then I add the pi. So these are my hunches, and as you will see, some were okay and some turn out to be turkeys. Now the types of tests I do is I generate 1 million sets of 10,000 random numbers with 10-digit random seeds. Okay, then I said, well, if I'm generating 1 million random numbers, I can actually take the first 6 decimals and go through every combination possible. I said, this sounds great. So I did that. I did 1 million sets of 10,000 with seeds an increment of 1/1,000,000 from 1 millionth to 1 millionth short of 1 million. And this test tests all the combination of 6 decimals. Results show actually high penalty factors. Why? Those trailing insignificant zeros were bad news. And once I saw that, I said, what if I cure that by testing the 6th decimal digit? If it's 0, then I don't use it. If it's not, if I have, if it is significant, then I include. This way I lost from here 9 to 10% of my data. Then I said, well, how do I cure this? I do a test. If the 6th decimal is 0, I add 1/10 of a millionth to the random number. So I end up, for example, 0.5 obviously has a lot of zeros. I add 5 zeros to it and then 1. So all the initial seeds were significant to 6 or 7 decimals. Just a summary, a brief look at the MATLAB barcode. This is the function that does the main testing and store stuff. Here it calls RNG 997 Gen 2, that's one version. C is the array of A and B. And the function returns the penalty factor and the initial random number that it generates. And here's the code for the function. And so basically, yeah. Here, for example, in the implementation of RNG Gen 2, I shuffle the seed and I get a random number through MATLAB, because I'm doing this like 1 million times. And that'll be my initial random seed. But notice here, this is the loop that calculates the subsequent random numbers, and I round to 10 digits, as I do here. And once I'm done, I calculate the factor for this series rounded to 10 digits. In this version, I do all 6. I try all combination of 6 decimals. Here, I generate the random number from just simply the loop counter and the maximum limit. And when I call another version of RNG 997, I give it C, which is the array of A and B, and the XRND. It's no longer truly random. I'm just marching and testing every one of those. This is the version where I check for all 6 significant digits. And here I calculate again the same way the random number. And then I calculate Z, which is 10 to the 5. And I say if Z mod 1 is greater than 0, we're good. Go ahead with the calculation. This way I lose about 9 to 10% from the million numbers that I'm anticipating. Here, I do the similar test, but instead of ignoring it, I just add 1e to the minus 7 and keep going. So I still get 1 million results. This is the results for our baseline, and this is very important. This is the 10-digit random seed test, and I focus on the lower and especially the upper limit. So I have one from 148.9 to 149.2. My goal is to get results that are in the upper limit is in the 147 dot something. If I get that, I'm happy. If I get 148, I'm not really happy, because I want to kind of give enough advantage to the algorithms over the 997. Here, when I use all random all digits and a lot of trailing zeros, it gets worse. And it gets a little bit better if I have 6 significant digits, and if I add e to the minus 7. So if you're going to use this baseline algorithm, make sure you are generous with your digits. This is the result for Angel Martin's algorithm that used in the random ROM, and as you can see, the upper limit for the mean is 147.8. So it's in the 147. Good. So if you use his algorithm, it's documented in his manual, you're in good shape. Now I look at the optimized algorithms with various ranges of B. And of course, since they are optimized, all these, the upper and lower limit values are way below 147. But that's only if you use these values, this initial seed and these values. But this stage serves for qualification of the algorithm. You can use this, and you can get very good sequence of random numbers if you want to, you know. And supposedly the Excel files included will show you other results, slightly worse, but still very good. And here we look at the 997 with pi at 10-digit random numbers. This is 147, but this is 148. I don't feel the love here. With 6 decimals with trailing zeros, again, it's not that much of an improvement. But there's an improvement if we have 6 significant decimals or add e to the minus 7. So this works better this way. And when I take the results for algorithm 1, if 10-digit seed, I get good results with the in the 147. If I have 6 decimals with trailing zeros, it becomes comparable to the 997, no big deal. It does improve better if I make all 6 decimals significant. And again here, it's a little bit. So these two approaches do well. Of course, you can always use these constants and get the 105, which is sort of the Cadillac of the random number series. Algorithm 2 makes a stellar success. As you can see, whatever I do, whether I do 10 digits, all 6 decimals willy-nilly, or 6 significant decimals, or add, they're all in the 147, which reflects the stability of this algorithm. And this algorithm is one of the stuff that I recommend. And these are the values of A and B. You don't have to worry about using these. You can just use these values of A and B. They're the same. The algorithm number 3 here, the upper limit is in the 148, so is the lower limit. I don't feel the love. It's teeny better than our baseline, but I'm not looking for a charity. So, I'm not impressed. Now, when I go to the 1003 times R, the 10-digit random seed does teeny better than the baseline 997, but in the other cases, it jumps and it does worse. So that algorithm is not. I was having high hopes for it. When I add pi, again, it's the 10-digit random seed does a little bit better, but I want this number to be in the 147. So again, that range is comparable, or here and here it's comparable to 997. Here it's slightly worse. So again, it's then I have the 11011. Again, here the 10-digit seed is somewhat comparable to the 997, and then here it kind of gets worse a little bit, and then it becomes comparable. So this is not super impressive. But when I add pi to it, the 10-digit random seeds do very well. The other ones actually do worse than the 997. So this is good. And when I do the 9977, it's terrible. I mean, even the lower is the 160, so that algorithm bombs out royally. If I add pi to it, the 10-digit random seed, that's so comparable to the 997 baseline, but the other versions, 6 decimals with insignificant zeros, with significant decimals, they all do much better. So that's good. We will come back and tally everything together. And the 9997 10-digit random seed, teeny better than the 997, but not the love that I'm looking for. And the same is true here. Here it does a bit worse because of the trading zeros with 6 decimals. And if I add pi to it, the 10-digit random seed does better. And actually, I think while the other versions do comparable to the 997, so the results as a minimum penalty factor belongs to actually pi plus 9997 times r. And you can use it with 10-digit random seed. And then this algorithm also here, you can use it with 10-digit random seed. This one, you can use it with this initial random seed. But the winner, the best stable algorithm is this one. And again, this one, pi plus 110011, you can use it with 10-digit random seed. But this one, you're comfortable. You can use it with fewer, 10 digits, fewer, 3-4 decimals, that's fine. So this is the results horizontally, the stat vertically. I'm going to transpose it and chop it into 2 slides. The best one is the 9997 plus pi, the random seed. But here, in order to get this good result, you need to put 10 digits initially. Then the 9977 plus pi, by adding e to the minus 7, does also very well. Then the algorithm 1 random seed 10 digits does well, followed by 9977 plus pi, okay, and then 997 plus pi, all decimals. Here it's the 6 significant decimals. Algorithm 2 here shows that it does well here with all decimals if we add e to the 1 e to the minus 7, and then it continues on the second page with 6 decimals and even 10-digit random seed. Again, Angel Martin's random ROM does well too. And then algorithm A with 6 decimals, 6 significant decimals does well. 997 plus pi does well by adding e to the minus 7, and then it does well with 6 decimals, and then the 11011 plus pi does well with the 10-digit random seed. Now the random optimization, the random search optimization, we use the same limits, a from 0 to 1 and so on, and then we have 3 intervals for B, same number of samples. Calculations take also long because I made the random search a lot because it was just searching blind. And this is the ranges for the parameters. Let's go to the results. Of course, algorithms 1, 2, and 3, and this is in the first phase, and then in the second phase, they do very well because these are optimized. And you can use these initial random numbers with these values and get very good random series. When we do the second stage results, algorithm 1 does well with 10 digits, and then if you add e to the minus 7, actually it doesn't do well. But algorithm 2 does well with a random seed Here I'm sorry. Here I'm comparing the worst, the best and worst. The best is giving a 10-digit seed, and the worst is sort of like only these two. So in this case, algorithm 2 in the both extreme does well. And that reinforces the conclusion we got from stage 1, that this is very good. The parameters values for A and B are slightly different, but not in orders of magnitude. And then, of course, algorithm 3, it's not in the range that I'm looking for. So this is algorithm 2, has the least upper confidence in the penalty factors. And this is, so you have two versions of algorithm 2 based on the optimization. You can choose the first one probably. And you are free to use fewer decimals, give it 10 decimals and so on. So the choice of use, you can use, this is the last slide, algorithm with specific X, R, and D, initial seed A and B. And you can get those small penalty factors, very good sequence of random numbers. The Excel files, like I said, has other values that you can look into. Use the algorithm with 10-digit random initial seeds. Make sure you supply at least 10-digit random seed and minimize the zeros. You can use the 6 decimal initial random seed, or even the 1e to the -7, the ones that showed promise. But again, algorithm, the second algorithm that I showed, that in both stages did well. So, thank you very much. Yes?
So in some of these algorithms, you recommended initial seed that perform really well, right?
Like in the 10-digit random seed, the random seed comes from MATLAB. I mean, I'm supposed to supply it, but I can't type a million whatever, and expect to finish in. So I let MATLAB do that standing in for
So
me.
you used MATLAB's random number generator.
Yeah, but the other ones, it was generating random numbers based on the loop counter. Like the first one was 1 million, and so on. And it would go on all the combination, test all the 6-digit combination.
Right. Well, my question is actually that some of them that there's a specific seed that you said with this seed it generate high quality.
Yeah, based on, because it's optimizing, it's saying what is the best value of A, B, and the initial seed that will give me good.
But my question is that because this algorithm doesn't distinguish the next number can also be a seed, right? Because it's generating the next number on the sequence of the previous number.
No, the first seed is initially is taking it from MATLAB.
Right.
But then it's calculating the rest and then rounding to 10 digits.
Right.
Yeah.
But my argument is that shouldn't every number on this sequence be as good as the seed as all the others?
Yeah, because this is saying what is it that gives you a good sequence? You're right. And if you are using just the initial seed and reusing it, what you can do sometimes is skip every other one so you don't have the same sequence. Yeah. The thing is, the whole sequence is good. That initial random seed, I'm saying, what initial random seed do I use or get to give me a good 10,000 sequence, with very good properties?
Is it going to remain good if I just never come back to this seed? I just keep going for
I don't know, because the penalty factor is a function of the number of random number it generates. If you make it, I think the bigger the more numbers you use, the smaller it gets, because the likelihood of patterns diminish. I used to use fewer numbers, so the numbers were higher. But I decided, for timing's sake, my computer would run a day and I would stop, that I would do a run of 10,000. That became fixed, yeah.
And the next question, did you test the MATLAB's random number generator? How good it is?
Oh, no, I don't know, because it's representing me it's standing for me, submitting random number. If I did that by hand, I would be finishing one run in a month or whatever, so.
But it's probably very good though, I'm sure, yeah.
It'd be good to compare it to with your methods, to compare that street to one of your other ones. Just see how good, how much better yours is.
It does, it used the twister, Mercine twister, which is very good, yeah. And I'm also telling it to reseed the
What is the useful, what's the term for the useful number that you think you can generate?
I'm sorry,
You have
Oh.
a random number generator, and you're gonna generate all the random numbers, but it's called the series length or something. How many random numbers is it good for?
I'm generating for 10,000. I'm assuming that if you, on the calculator, you won't need more than 10,000 random numbers. Yeah.
So that wasn't even a consideration.
Because I'm thinking it's for the calculator. I'm using MATLAB, yes, and I'm rounding down so that it will work with the calculators. In 2017, I did not round down. And after that, I realized, that's the problem of the accuracy. I remember in 2017, I was very creative and I did fancy equations, and I decided to come back and just do something simple and see the variation in that simple and rounding down. Yeah, I was very mindful of that. So, okay, thank you.
Thank you, Namir.